Hi, welcome back to Mrs. Thompson's classroom. Today we are going to talk about solving equations. This is part one of this unit. We are going to be talking specifically about linear equations in one variable, and we'll talk about the different types based on the type of solutions they have. But first we're going to start with a little vocabulary of equations in general. So let's talk about what the domain of an equation is. The domain of an equation is the set of all possible solution values. In other words, it's the set of numbers that could even possibly work in that equation. So things that would not be in the domain would be any number that would make it just undefined. So for instance, for a linear equation, pretty much the domain would be all reals. But if we were dealing with an equation that had a fraction in it, where the variable was in the denominator, well, we can't divide by 0. So any value that would make the denominator 0 is thrown out as possible, and so it would not be included in the domain. Okay, there are a number of equations whose domain is all reals, and that's what we're going to be dealing with today, because linear equations have a domain of all reals. Now, a solution is a value for the variable that makes the equation true. Okay, and you'll see we can also call that a root of the equation. Okay, the solution set is the set of all solutions. So some equations will have multiple solutions, and so we could write the full set of all of them. Okay, an identity is an equation that is always true. Okay, so this is something that would be considered a rule. Like in science class, you might call this a law because it's just always true all the time. So just a statement like 1 equals 1 or the square root of 4 equals 2. Those are identities that are true. Now, neither of those have variables in them, but there are equations even with a variable that turn out it doesn't matter what x is, the equation always comes out to be true. So we would call those an identity. For in the world of right triangles, for instance, a squared plus b squared is always c squared. We know that's the Pythagorean theorem. It's always true in the world of right triangles. And so that's an identity for right triangles. A conditional equation has a finite solution set. So there is just a set of numbers. I could list them out. You know, it might be one solution, it might be 10, but I could make a list of all the numbers that make that equation true. An inconsistent equation has no solution. So it is never true. Okay. And equivalent equations have the same solution set. So for instance, 2x equals 10 and 3x equals 15. Both of these have a solution set that is x equals 5. So they are equivalent equations. Okay? All right, now let's spend a little time actually solving some of these equations. So the first, we need to know the objective. The objective is to get down to x equals a number. So we need to get all the x's together and we need to get them all by themselves. So the first thing I'm going to do is I'm going to use the distributive property. Okay, so I'm going to distribute the 5. So that will give me 5x minus 15. And I'm going to distribute the 4, so that'll give me 4x plus 4. Then I'm going to combine like terms. And so this will give me 8x minus 15 equals 4x plus 4. Now I need to get those x's together. So I'm going to subtract 4x from this side so that this goes to 0. But whatever I do to the right, I have to do to the left. That's the golden rule of equations. So this is actually our additive or addition property of equality. And you can do this with addition, subtraction, multiplication, division, as long as you do the same thing to the left that you do to the right. So this gives me 4x minus 15 equals 4. So now I need to move the 15 so that I can get the x by itself. So I'm going to add 15. So I end up with 4x equals 19. Okay, if I bring this up here. So now I'm going to use the multiplicative property of equality. And I'm going to multiply by a fourth, which is the same thing as dividing by 4. And I'm left with 1x equals 19 fourths. So this is my solution. And if I want to write it like a set, I could do like this. Okay, but x would equal 19 fourths. That's the only solution. That makes this a conditional equation because it has a singular solution. It has a finite solution set. Okay, let's try this again. So I'm going to distribute. We'll try to work through this one a little bit quicker. So I'm going to distribute. Then I'm going to combine like terms. So 4y and 2y make 6. Negative 8 plus 2 makes negative 6. Okay, now if I want to get those y's together, I'm going to use that additive property of equality. And I'm going to subtract 6 so that this goes to 0. But that means this also goes to 0. So the only thing left is negative 6 equals 4. So the variables all went away. So it doesn't matter what y equals. I get negative 6 equals 4. Well, that is false. That's never true. Okay, so that makes this an inconsistent which means there is no solution, or the solution set is the empty set. Okay, there's no solution. All right, let's try one more. Distribute, so I get 3x plus 3 times 2, which is 6. I'm going to get 4x plus 4 times 2, which is 8. And then I got to distribute this negative through here as well. So it's like multiplying by negative 1. So I get negative x minus 2. Combine like terms. And I end up getting the exact same thing on both sides. Okay. So from right there, I see that the left is equal to the right. So that means this is always going to be true. If I want to further clarify that, I can use that property of equality and I can subtract 3x. That goes to 0, leaves me with 6 on the right. But that means I have to do the same thing on the left, and those go away, which leaves me 6 on the left. So this is always true. Okay. So this means this is an identity. And its solution set is going to be all x such that x is an element of the real numbers. Okay, or that would be negative infinity to infinity if you want to write it as an interval. Okay, so it has an infinite number of solutions. It is true regardless of what value of x I put in there. And you could try a couple. You could plug in 1 for x, plug in a 2, plug in a 3, and try it. But you'd have to try from here to infinity to actually prove it that way. So the better thing to do is just do the work and show it by doing the process of simplification. Okay? So hopefully this helps. In the next couple of lessons, we'll expand and we'll do quadratic equations and higher order equations. We'll even do some rational and radical equations and some absolute values. So we're going to kind of expand, but all of them have this possibility of being identities, inconsistent, or conditional. So we'll keep that in mind through the whole process. Okay? All right. We'll see you next time. Hopefully this helped, and we'll see you then.